Okay, we're working on Chapter 3, Numbers in the Real World. This is from the Bennett and Briggs portion of the book, which is the back of the book. And we're looking at Section 3A, the uses and abuses of percentages. But we're going to start off by looking at how to express fractions as decimals and a percentage, something we've looked at before, so this is just a quick reminder. When you want to take a fraction like 2/3 and change that into a decimal and a percent, then to get to the decimal, you just want to do the division. So we can just do that on our calculator when these come up. So we want to just take the 2/3, enter that in as 2 divided by 3, we get 0.6 repeating. When I'm going to take a fraction to a decimal for the purpose of going to a percentage, I like to use 4 decimal places. We had a whole bunch of 6s, so this was a 6, but the next digit was also a 6, so when I stop I'd round that up to a 7. And then, as we saw in previous portions of the book, when you want to make that a percentage, you multiply by 100%, or you move the decimal over 2 places and add the percentage symbol. So 66.67%. So we're going to do that for a couple more. We'll go ahead and slide this over so we can look at both of those together. So 5/8 would be 0.625. Now that one I didn't have to round, so I didn't have to think about how many decimals, just put exactly what I saw. Multiply by 100%, that moves the decimal over 2 from multiplying by the 100%. Go ahead and write this one out. Oops, 100% times 0.625 is 62.5%. 100% is 1, so you're not changing the number, you're just changing the way it looks. The 100 moves the decimal over 2, and then we have the percent symbol on there. So 19/13 is approximately 1.4615. If I do that a little more clearly this time, times 100%. The 100 moves the decimal over 2 spots, so 146.15, and then we also have the percent symbol. Again, 100% is a whole, so when I multiply by 100%, I'm multiplying by 1, not really changing the value, just changing the way it looks. All right, so let's move into a couple examples that use that skill. So express the first number as a percentage of the second number. 120 million metric tons of beef produced annually in the US out of 65.1 million metric tons of beef produced annually in the world. So they want the first number as a percentage of the second. When they want that, you take the first one and you divide that by the second one. So if you think about that, that's just like what we were doing up above. So we'll do that with the same technique. Bring in the calculator, do the 12.0 divided by 65.1. Comes out messy, so we'll round that to 4 decimal places, 0.1843. Multiply by 100%, which I won't write out this time, but just moving the decimal over 2 spots and adding the percent symbol. So 18.43% of the beef produced in the world is produced in the US, is the way we could interpret that. And then just another one very similar. Express the first number as a percentage of the second. An estimated 10,000 US nuclear weapons out of an estimated 27,000 worldwide. So same idea, a little scarier topic, but same idea. 10,000 in the US divided by 27,000 worldwide. Go to a decimal first. We get approximately 0.3704. So notice that when I do that division, our 4th decimal place actually a 3, but followed by a 7, so I rounded that up. Multiplying by 100% moves the decimal over 2 spots. We add the percentage symbol, and there we go. So apparently 37.04% of the nuclear weapons in the world are in the US. So that's our technique. If they want the percentage of one number, they want the first number as a percentage of the second, do the first one divided by the second, that gives you a decimal, which we can convert to a percentage. Okay, so on the previous page we saw some of the basics of converting a fraction to a percentage, and now we want to go ahead and look at some applications of that and some kind of trickier thoughts to look at perhaps. So between 2000 and 2010, the population of Las Vegas increased from 478,000 people to 565,000 people. And over the same decade, the population of Los Angeles increased from 3,695,000 to 3,793,000. So which city had the greater absolute growth in population? So we're going to answer that, but I'm just going to pop down to the bottom and show you the definition of that. So absolute change, which is what they're asking about, describes the actual increase or decrease from a reference value to a new value. And the way you compute it, absolute change, is to take whatever the more current value is and subtract the reference value. So a lot of times they refer to this one as the new value. A lot of times this reference value will be an older value or an old value, and that's the case here. So let's go ahead and look at the absolute growth for both of these two cities. So starting out with Las Vegas, the absolute change would be the new value for the population in Las Vegas, 565,000, minus the older value, 478,000. And I'll just do that subtraction off on the side on the calculator. So 565,000 minus 478,000 is 87,000. And it's good to think about what the units are on this. So this was people, that's people. We're subtracting, so it'd be 87,000 people. And the other thing that's worth noting is because the older value was smaller, this was an increase of 87,000 people. So the population of Las Vegas over this 10-year period grew by 87,000 people. So how's that compared to LA? So we do the same thing. We'd take the more current number, 3,793,000, and we would subtract the older one, 3,695,000. And let me do that off on the side, see what we get. And that's 98,000. And again, that's also people. And again, the older number was the smaller one, so that's also an increase. So a fairly straightforward answer to their question, which city had the greater absolute growth in population? Las Vegas grew by 87,000 people. LA grew by 98,000, so LA had the larger absolute growth. Okay, so on the question we just did about absolute growth, I believe that we gave the correct answer, that LA really did have the larger absolute growth. However, if somebody asked me which of these two cities was growing faster, I don't think I would say it was LA. And that's because if somebody asked me that question, I would probably think about how much of a percentage growth that city was having. And that's the other question they want us to answer here. Which of the cities had the greater percentage growth in population? That's similar. You still want to do the subtraction of new value minus the reference or the old value to come up with the absolute change. But then to make it a percentage, you divide by the reference. And so if you look at that, the reference one is the older one, right? So when we turn this into a percentage, we're usually going to divide by the older value. If somebody asks you for the percentage change, you'll just do this relative change, which is actually a decimal, and then you can multiply by 100%, and that'll give you a percentage change. Sometimes you'll subtract and divide all at once, or like in this case, we already did the subtraction for part A, so we'll just take our answer and divide. So let's go ahead and go back to this again and try and apply that. So which city had the greatest percentage growth in population? So for Las Vegas, we saw above, they grew by 87,000 people. And we're supposed to divide by the reference or the older number, which was the 478,000. And we're going to see how does that compare with what happened in LA, where they grew by more people, 98,000, but our reference number is a larger 3,695,000. So when we go to a decimal, that'll be something we could then convert to a percent. So let's slide this over, look at that work on the calculator. So 87,000. And I'm going to show you something here real quick. You can put the zeros, or you can skip the zeros as long as it's the same number of zeros. The zeros on the 3 zeros top and bottom is like multiplying this one top and bottom by 1,000, which wouldn't change the decimal. So if you notice an equal number of zeros on top and bottom and you want to save a little time, you can just drop them off. So this would be 0.1820, and multiplying by 100%, that becomes 18.20% growth for Las Vegas. But if you take the 98,000 divided by 3,695,000, you get a much smaller decimal, 0.0265, and multiplying by 100%, move the decimal over 2 and add the percentage symbol, and we get 2.65% growth. So even though LA added more people, I would say Las Vegas is growing faster because it added almost as many people, even though it was a much smaller city at the start of that decade. So Las Vegas has the larger percentage growth, or the greater percentage growth. And then just another quick thought. If they had only asked which city had the greater percentage growth, you would have the option of doing the absolute growth calculation first and then doing the division, but you could also do it all at once. So let me just show you what that would look like for Las Vegas. I would take the 565 newer value minus the 478 older value. I'd make sure I put that in parentheses, and then I would divide by the older value, 478,000. So in parentheses, I'm calculating the absolute change, and then I'm dividing by the reference number, which takes me straight to that decimal. So you can actually get there a little quicker if that's your only thing you need is the percentage growth. You could go straight there. But if you do that subtraction in the division all at once, make sure you put parentheses around the subtraction. All right, so there's that summary of absolute and relative change. Absolute change is just a subtraction of newer minus older. When you want to do relative change, you take that difference and divide, but make sure you're dividing by the older reference value. And just a quick note about units. Here the units were people, and in other applications maybe it would be dollars or feet or pounds. But when you go to percentage growth or the relative change, you're always changing those units from whatever they were originally, people, pounds, dollars, to percentages. So you have consistent units on percentage change or relative change, but absolute change will always be the original units of the problem. All right, continuing down that same line, let's look at another example. The congressional delegation of California increased from 30 in 1950 to 53 in 2010. What's the absolute change? So we want to do the newer number, 53, minus the older number, which is 30. The difference there would be 23, and it would be whatever the original units were. It's the congressional delegation, so we might say delegates. And I believe that, if you're wondering, like, what is that? I think that's our 2 senators plus the number of people that go in Congress. Don't quote me on that in your history, but I think that's what they're talking about. Now, when we go to do the percentage change, we'd take that absolute change of 23, and we would either divide it by the 30 or the 53. So if you look back at that definition on the previous page, we're supposed to divide by the older number, which would be 30. And if you do that 23 over 30, let's see what we get. So 23 over 30 is approximately 0.7667. Moving that over 2 spots and adding the percentage, 76.67%. So it's been a huge increase for California from 1950 to 2010. If it was a 100% increase, that would mean it had doubled, so it's almost doubled since then. But I want you to see that if you pick the wrong number, it's a much different answer. If I took that same 23, but I divided by 53 instead, I get 0.43396, so somewhere around 43%, which is almost only half of this growth. So it's really important that when you're calculating percent change, you don't just grab one of the two numbers. You have to get the reference number correct, and in something chronological like this, you want to look at the older value. All right, so moving forward, let's look at another percentage application. The 2009 life expectancy in Canada was 81.2 years old, and that is what percent greater than the 2009 life expectancy in Russia. So it's the same thing here, where we're going to want to do a difference and then division to get the percentage of change, or in this case the percent greater that one is than the other. But it's not like we would think of one of these as newer or older than the other. When you're trying to do a reference number and they're comparing two things like Canada to Russia, the reference number is the one that you're comparing to, or that would come second in the comparison sentence. So we're comparing Canada to Russia, so that makes Russia the reference number. So when I do the percent change, I want to do the new one that I'm comparing with, Canada, so that's 81.2 years old, and subtract the reference number, Russia, 65.9, and then when I divide, I want to make sure that I'm dividing by the reference number, which is 65.9. Notice since they're only asking for what percent greater is it, I'm going straight to percentage change, and so I'm going to do that all at once in my calculator. But when I do that, I have to remember that this subtraction needs to be in parentheses in my calculator, otherwise that's not going to come out right. So let's bring the calculator in and open parentheses, 81.2 minus 65.9, close the parentheses, that's the end of the numerator, and divide by 65.9. That'll give us a decimal first, 0.23, sorry about that, 32322. And they want the percent greater, so we do times 100%, which really means we're multiplying by 1, not changing the value, just the way it looks. The 100 moves the decimal over 2 spots, and then we put the percentage symbol on. So apparently, the life expectancy in Canada, which is 81.2 years, is 23.22%. And I won't write the percent symbol because I already had the word there, right? So that would be duplicate. Greater than the life expectancy in Russia. And it's interesting to note that if that's what happens if the Canadians are being compared to the Russians, if the Russians were being compared to the Canadians, we would do the subtraction in a different order, 65.9 minus 81.2. But because we're comparing two Canadians, they would become the reference, and we would divide by 81.2. And this would mean that it's a shorter lifespan, so it's 18.84% shorter lifespan in Russia than it is in Canada. So it's interesting that it's not just the same amount. It really does matter which group is being compared to which, because you always divide by the one you're comparing to, and that changes your percentage. So another example of that sort of thing, the area of Norway is 24% more than the area of Colorado. So Norway's area is, and they want a percentage here, of Colorado's area. So they're trying to figure out how to do a translation. How do you change 24% more than, which sounds like addition, to some percentage of, which sounds like multiplication? So we're trying to figure out what is the translation that makes the equivalency between a percent more than addition to a percentage of, which is multiplication. So it turns out that the answer to that question is provided for us right down here in this box, that if you want to go from p% more than to an of, so here's the of and there's the more than, then what you want to do is whatever the p% is, you add that onto 100, and that's what it would be for the of. So if I just try and follow that pattern up here, they said 24% more than, so I would take 100 plus their 24, and that percent would be what the of is. So that becomes 124% of. So that's what I'm going to go ahead and fill in there. So the area of Norway is 24% more than the area of Colorado, so Norway's area is 124% of Colorado's area. And this is going to be a really important translation for us as we move forward, so we want to get used to that. And I would point out a third stage of this too, which is if it's 124% of, that's the same as 1.24 times. So we really want this to be 3 levels, not just 2. P% more than is the same as 100 plus P% of, and then if you change this to a decimal, you'll get the times. So we want to be able to go from here to there as well. And I'd just like to show you that real quick. If you did 20% more than, let's just make up a number for our starting thing. Let's say it was 150. 24% of that would be 0.24. And if it was going to be that 24% more than the original, that would be 150 plus that 24%. Sorry, I got that number wrong. 150 plus 36 would be 186. And my claim is that calculating 24% and adding it on to the original, doing that right here, would be the same as just taking the original times 1.24. So let's try that. 150 times 1.24, and we get the same number. So I'll show you that again and again as we do other examples, but we want to make sure we have that down because we use it all the time in later chapters. So 24% more than is 124% of, or 1.24 times. Now if we're doing a less than instead, it's the same idea. You would just subtract it away, and we'll see an example of that on the next page. All right, moving on to another example. A store is having a 40% off sale, therefore the price is blank of the original price. So this is just like what we were trying to do a moment ago with the Colorado and Norway thing, except for when they say 40% off, that's 40% less than. And so we're going to go to this idea right here that if you want a percent less than, subtract that away from 100 and you could do that percentage of. So let's go ahead and take a look at what that would mean. You would do 100% and then you would subtract the 40% because that's a discount, and that would leave 60% left over. So the claim up here is that subtracting off 40% of the original price is the same as multiplying or taking 60% of that original price. So we can use that to get a quick answer for the question that follows. The sale price for an item with a regular cost of $80 is what? So the quick way to do that would be to say 40% off is the same as 60% of 80, and 60% of 80 would be 0.60 times 80. And if we multiply that out by hand or on the calculator, we get 48 or $48. And that would be a quick way to compute the sale price. So the sale price is $48. Now most people don't do it that way. What most people would do is to think about, okay, the price is 80. Let me clear this other stuff out. We have that price of 80, but it's 40% off. So take that 80 times 0.40 and you'd be saving $32. So take that $32, subtract it from the original amount, and you get 48. But notice that method that uses subtraction can be done in one step through multiplication. If we just convert that 40% off to 60% of, then we get the quick multiplication problem and we finish a little faster on that. And not only is it a little faster, but like I said on the previous problem, in later chapters in the book, we have to be good at figuring out how to take a percent more or a percent less than and quickly change that to a multiplier. So we need to learn that if something's going down 40%, that's the same as multiplying by 0.6. It takes a little practice, but it is going to be an important skill for us. All right, let's go ahead and take a look at another example, a little different this time. The percentage of fifth graders who scored at or above the national average on the reading test rose to 44% from 25%. So describe this as an absolute change and also describe it as a percentage change. So this is a little bit of a tricky one because when we do absolute change, the units are whatever the original units are, which is percentage. When we do relative change, that becomes a percentage change and always has units of percentage. So these are going to have the same units. That's not typical. Typically, this would be like people, and this would be percentage. Or this would be dollars, and this would be percentage. So when you're talking about percentages, absolute change and relative change can be kind of confusing because they both have the same units, but you follow the same procedure we learned before. If you want the absolute change, you would take the newer value minus the older, and they rose to this newer from that older. So we would do the new value, 44%, minus the older one, 25%, and the difference on that, just double check, I believe is 19, but play it safe. Yep. So 19% is the absolute change. Now if somebody asks, well, what is that as a relative change? We'd take the difference, 19%, divide it by whatever the older or reference number was, which was 25%. So we do that division, we'll get a decimal. And when you do that division, percent over percent, the old units go away and we just get a decimal. But then we multiply that by 100% and we get 76%, which brings the percentages back in again. So it's a little tricky to talk about this. So the reading scores got better. Did they get better by 19%? Or did they get better by 76%? And it's a little tricky, but it's both. They got better by 19 percentage points, which is how much we added on to the old value. But they are 76% better than what they used to be, which is more of a kind of multiplication look at it. So people aren't as careful with this as they should be, and that makes it confusing to differentiate between these. So the book has advice for us here, which unfortunately not all people in the world follow, but this is a way you could theoretically be able to tell the difference between those two. When you see a change or difference expressed in percentage points, then you can assume it was absolute change, which is addition subtraction. If it's expressed with the percentage sign or the word percent, then it should be thought of as the relative change or difference. So a relative change or relative difference. So what they're saying is, instead of saying 19%, what we should say here for clarity is that it was 19 percentage points higher. And that if we phrased it that way, that would clarify that this is an addition of 19% on top of the previous 25 to get to the new level of 44. Unfortunately, people are very careless with this and they don't do this. They just do percent all the time. So my advice for you here would be that you should try to express it in the correct way, but also you should be careful when somebody says that something's 19% higher than it used to be. You need to ask them, do you mean like adding 19% to what it used to be, or doing a division of the increase divided by the old to get like a relative increase? Because it's a big difference, right? Think about like if you were the teachers here trying to report the success of your program, would you rather say it was 19% better or 76% better? Right? This sounds better, but they're both true, and you should give the answer that people are looking for. Do they want to know what percentage you added on to the old percentage, or how the increase compares to where you started? So it can be a tricky thing when you're doing percentage to begin with and then start talking about relative change. So in those cases, always just slow down, think about what is trying to be expressed, especially if somebody else is trying to convince you of something. Don't let them trick you by picking a more favorable number than they should. Let's go ahead and take a look at another problem that points out how percentages can be misinterpreted sometimes because people are a little bit careless about talking about percentage of versus percentage above or more than. So the average annual precipitation on Mount Washington, New Hampshire is 90 inches. During one particularly wet year, different news reports carried the following statements. One report said the precipitation this year is 200% of normal, and the other one says the precipitation this year is 200% above normal. So you had maybe two different reporters talking about it two different ways, but are they saying the same thing or are they saying different things? So what does each of these statements imply about the precipitation during that year, and do they mean the same thing? So let's look at 200% of normal. So 200% of normal. So if I translate that, 200% of normal means 200% of 90 inches, because 90 inches is the normal for Mount Washington. And then when we go to do the math on this, you change the 200% to a decimal by moving 2 spots to the left with your decimal and have 2.00. The of becomes multiplication, so times 90. So this is just 2 times 90. We do the math on that, we get 180 inches. So if the first reporter, sorry, missed an H there, if the first reporter is correct, then there was 180 inches of rain in Mount Washington that year. Now let's look at the other phrasing, 200% above normal. So above means that we're adding to normal. So you would start with normal, and then you would add 200% of normal. And if we plug in the 90 there, it's 90 plus 2.00 of, or times 90. And this time we get the 180, but added that on top of the normal, and we'd get 270 inches. So do the two statements have the same meaning? No, not the same. A lot of times when I'm teaching this in class, face-to-face, people will ask me, well, which one was it really? And I don't know. You can go do some internet research on Mount Washington, New Hampshire, I guess. But the point is that both of these people thought they were saying something completely fine, but they weren't being careful between the difference between percent of normal and percent above normal. So again, my message to you there is just you have to pay attention. It's not the same. Percent of is straight to a multiplication. Percentage above, you might still multiply, but you're going to add that on to the original, so it's definitely different. All right, let's take a look at another example. The final cost of your new shoes is $107.69. Look at you spending 100 and something on a pair of shoes. The local sales tax rate is 6.2%. What was the retail pre-tax price? If you want to challenge yourself here, try and just stop the video and figure this out. When I ask people in class to do that, often they get it wrong. So you can kind of see if you fall into that same boat or if you are a step ahead. But it is a little bit tricky. So pause that and give it a try. And I'm going to go ahead and jump back in now and show you how I would do it. So when people get this wrong, I'll show you what they usually do. They hear the sales tax rate is 6.2%. And so they take the 6.2% and they make it a decimal, 0.062. And they multiply that times 107.69. And that's actually the mistake right there, because this is not what the original price was, and the sales tax rate is supposed to be applied to the original price. But we don't know what that is, so people just apply it to that number instead. And then they take the 107.69 and they maybe round that to the nearest penny, and they subtract that away, and they say probably $101.01. But it turns out that is wrong. So let me show you how to do it, and I'm going to show you a way that involves a little bit of algebra. So I don't know what the original price is, the pre-tax or retail price. So I'm going to let X be equal to that retail price. And then I'm going to think about some pieces. So how much would you pay in tax? So the tax is 6.2%. So let's write this out. The tax is 6.2% of retail. And that means that the tax would be 0.062, converting that to a decimal, of times the retail price, which we don't know, so that would be X. And then we have a total, and the total is $107.69. So if you want to make an equation out of this, how do you get to the total? You take what it says on the price tag, you add tax, and that's your total. So that would be, so let's fence this off. So my equation would be the original price plus the tax is equal to the total. When people, another mistake people make sometimes is when they add the tax, they just want to add 0.062 because it says that's the tax rate. But the tax rate is always multiplied times the price. If you don't put that X there, you're just adding 6 cents, 6.2 cents to every purchase, which would be awesome, right? When you buy something really expensive, tax is just 6 cents, but it's not. It's 6% of whatever the price was. So now when you go to finish this off, we're just going to use our normal equation techniques. It's just a little messier because of the decimal. But one important thing to think about is these are like terms, so you want to combine them by adding the coefficients. So if there's no coefficient visible, you have to remember that means it's 1. So if this was 1x and 8x, it'd be 9x, right? We just add them together, add the coefficients together. So you do the same thing even if one of them's a decimal. So you have the coefficient from here, 1, plus the coefficient from there, 0.062, and that should just be the 1 and the 0 added together, 1.062. So you don't really need the calculator on that, but that's what it would look like. So 1.062 times x, that's combining these two, is 107.69. And then you divide by the coefficient of x to get x by itself. So we'll divide both sides by 1.062. So x is approximately, let's see what we get, 107.69 divided by 1.062 is actually $101.40, which is a little different than what people often get when they apply the percentage 0.062 to this number instead of to the unknown. So it does make a difference. In this case, not a big difference, but sometimes it can be a really big difference. Sorry, couldn't see that answer there. 101.40. So make sure we answer the question. Go back up here. What was the retail price? It was $101.40. And then I just want to point out something else. This is a plus, so it's a more than, right? So you see that 6.2% more than the original, we did addition. But notice when we combine like terms, that became 1.062 times. So we see that again, that statement they had a page or two back, where adding 6.2% is the same as multiplying by 106.2%, or 1.062. So we're using that addition to multiplication as kind of happening here in our equation, but it's also something we'll use again in later chapters. So this box right here kind of summarizes some tricks that you could use to do problems like the tax one. I think it's best to use algebra the way I just did it. The author from the back of the book is not assuming algebra. So they're showing us a trick. The reference value on a purchase price is the original value. So you would take the compared value, which is the afterwards part, and divide by 100 plus p. If we brought in that last part, you'll see that we ended up ultimately taking 107.69, which was the compared value, and dividing by 1.062, which is like 106.2%. So I think it's best to use algebra, and I'm going to do that on the examples, but you might see them do this trick with 100 plus p to solve some of those problems a little faster. But I would recommend the algebra. And if it was a discount instead of a tax, you'd use 100 minus p instead of 100 plus p. So let me show you a couple other percentage things before we wrap up the section. The number of housing foreclosures in 2008 was 3.98 million, and they say that was up 81% over 2007. So how many foreclosures were there in 2007? So 2007 is the older number, so it's the reference number, and yet they're saying how many, so we don't know what it is. And it's very awkward to not know what your reference number is. So you could use these tricks, but I'm going to show you algebra. Let's let x equal the number of foreclosures in 2007. And then let's think about what they're saying here. That's up 81% over 2007, or this 3.98 was up 81% over 2007. So the 2008 amount was 81% over, which sounds like addition. And I want to show you that trick. 81% over is the same as 181% of. So 81% more than or over is the same as 181% of. And I want to use that to get a little bit of a faster jump on my equation. And they're saying to do that here too, right? The 100 plus p. So going back to here, this number, 3.98, trying to just translate now, was or is 3.98, and what is that? That's 81% over the old value, which is 181%, or 1.81 times the old value. And the old value is an unknown, so that would be x. So the key step here, we'll do the algebra to finish this off in a second, but when they said 81% more, I'm saying that's 181% of, and that's of what? Of the older reference value, which was our x. So 1.81 times the old value is equal to the new value. And then the algebra to finish it off is just to divide both sides by 1.81. And so x, which is the number of foreclosures back in 2007, comes from 3.98 divided by 1.81. And let's see, they gave 2 decimals, so I'll just do that too. So that'd be 2.20. And then 2.20 what? So that would be the same as what the units were on this, which was million. So 2.20 million. I see that. I think maybe it's money. Wish it was my money, but it's not. It was foreclosures. So 2.20 million foreclosures in what year? X was in 2007. I would highly recommend that anytime your reference number, the older one that you're trying to compare to, pre-tax or an older year, whenever that's unknown, let X be a fill-in for that, so that when it comes time to take a percentage of the reference, you have something to write in that reference spot, which would be the X. Let's look at one more. Your dinner bill is $42.50, and you leave a $50, you just leave $50 on there and then you leave. So what percent tip did you leave? And just pretend we're in a state here where they don't charge taxes on food. So let's see. I think the first thing we should do is just figure out what is the tip. So if the bill said $42.50 and you put $50 on there, then the difference is the tip. Right? Subtract out the $42.50 that goes to the restaurant, and that leaves $7.50 that goes to your server. So we now know how much the tip is, but generally, servers in restaurants don't consider whether your tip was good or bad based on how many dollars it was, but based on what percentage it was. So to figure out the percentage of that tip, you would want to take the 7.50 and divide it by the reference. But we have an issue. Is the reference 50 or is the reference 42.50? And it would be the older one. So this is what came first, was the bill, and then later we put the 50. So this would be our older or reference value. And so when you're trying to think what percent tip that is, you take the $7.50 you left as a tip, you would divide it by the $42.50. That looks like a bit of a messy one, so bring in the calculator. 7.50 divided by 42.50 is 0.1765. Moving the decimal over 2 spots and putting the percentage symbol on, we'd have a 17.65% tip. And you can talk to the servers you know about that, see if that's good or bad. I do know this: if you go into a restaurant with a large party, like maybe you go in and there's 12 of you or something, a lot of times they'll put an automatic tip on the bill. And what I see most of the time is that they put 18%. So I would say that if you tip $7.50 on that $42.50, you're coming in right around 18%, which I guess would be pretty standard in the sense that that's what the restaurant would put as a default on a large party. All right. The tax on your dinner bill was 9.75%, and then you added a 20% tip to the pre-tax amount. The total amount after tax and tip was $62.06. Find the amount of the bill before tax and tip and use an equation and show your work. So what I'm going to start off with is looking at what they want me to find. They want me to find the amount of the bill before tax and tip. And so if I'm going to use algebra and an equation, I'm going to let x be the unknown, so I'm going to let x equal the amount. And just for clarity, I'll put all of the rest of that. It's the amount before tax and tip. So clearly then that's not $62.06 because this is after tax and tip. So now I want to think about how I'm going to get to that $62.06. I'm going to have to pay for the dinner, so I'm going to have to pay this amount. I'm also going to have to pay tax. So what would the tax be? Well, the tax is 9.75% of the price, so that would be 0.0975, which is the 9.75% written in decimal form, and then of the price would be of the pre-tax and tip price, so that would be of x or times x. And then I'd do the same thing with the tip. The tip is 20%, so in decimal form that would be 0.20, and that's 20% of the amount before tax and tip, so 20% of or times X. So then, what is this 6206? That's the total of all three of these things, so I'll label that as well. The total is $62.06. And the word total implies that would come from adding up all three of these. So you add the amount you owe for the food, plus the amount you owe for tax, plus the amount for tip, and that's the grand total of $62.06. And that seems right because this is the total after. So after adding those two things on. So if you look at the equation, then you would take the x, and then you would add on the 0.0975x, and then you would add on the tip of 20% x, and when you add all that together, that would be the total of 62.06. And now this is my equation. I want to solve it. When I solve for x, I'll know the amount of the bill before tax and tip. So I have three x terms here, 1, 2, 3, and I want to combine those. When you combine like terms, you always add the coefficients. The coefficient when you don't see one is a 1. So I want to add the three of those together. So if this was 1x plus 8x plus 9x, I would just add those up, 1 plus 8 plus 9, and have 18x. The rule is the same if it's decimals. So the first coefficient is 1, plus the second coefficient 0.975, plus the third coefficient 0.20. If I add those together, that gives me the total 1.2975. That's of all the coefficients, but it would still be x, just like 3x plus 5x is 8x. When you add all these together, it just tells you the new coefficient of x. And then that's equal to 6206. And we're trying to solve for x. This piece right here is connected by multiplication, so I'll divide both sides by 1.2975. That will cause this to cancel on both sides, and then I can do the division to figure out what x is. 62.06 divided by 1.2975, and since this is money, I would round it to the nearest penny, so x is $47.83. So it looks like the dinner bill probably said $47.83, and then by the time we got done adding the tax and the tip, we ended up paying $62.06. Alright, next question, how much was the tip? So we can just go back to this. It says the tip was 20% of the pre-tax amount. We now know what the pre-tax amount was, and we even had it labeled here. The tip is 0.20x. So let me just start off by copying that. The tip is 20% of whatever x is, but we just found out that x was $47.83. So now we just want to do that multiplication, and we'll know how generous we were with the tip. So 0.20 times 47.83 would be 9.566, but it has to be to a penny, so around the nearest penny, and that would be a tip of $9.57. And so now we know how much the tip was, and let's go ahead and see what the last question is. How much would the tip have been if you tipped 20% of the total bill, including tax? So what we're saying up here is that our bill had an amount of $47.83, but that wasn't the total on the bill. There was also some tax added in. So this is what the tip would be if you took 20% of the pre-tax amount. But a lot of people will look at the grand total on their bill and tip based on that, and I want to see how that would be different. To see how that would be different, I would have to know what that bill said. And to do that, I need to know how much the tax was. So to figure out the tax, I do 0.0975 times x. And we know from up above that the value of x was $47.83. And let's see what that is on the calculator. So 0.0975 times the $47.83. And rounding it to the nearest penny would be $4.66 in tax. So then what was the actual bill that we saw when we went to pay? That would have been the pre-tax amount plus the tax, but not our tip yet. So the total on the bill before tax, or sorry, before tip would have been the amount of the food, $47.83, plus the tax, $4.66, and let's add that up and see what the bill said. $52.49. And if we decided to make our tip based on that, so we'll call this a new tip because it's a different calculation than the one above. If we decided to do 20% of the total of tax and the original bill, it'd be 20% of $52.49. And let's see if that would be the same or different as doing it before tax. So bring the calculator in one more time. 20% of $52.49 is $10.50 if I round that to the nearest penny. So it is different. And if you look at what we had done originally, it was $9.57. So if you take that $10.50 minus the $9.57, it's about an extra dollar if you do the tip after the tax has been applied. So either way is fine. This is what officially, when, like, if you see a bill where the tip is computed by the restaurant, they'll do it on the pre-tax amount, and then this is the way most people do it. And I'm sure your server doesn't mind this at all because they're getting about an extra dollar out of it on a bill of $47. All right, that concludes section 3A.